and we had several options. The simplest one of them was to stop using memory mapped files in EventStoreDB. It's not the simplest one, but the most straightforward one, I would say. So this was easy to do for checkpoint files, but we had also recently implemented a Bloom filter data structure that also used memory mapped files. And for this one, it was going to be harder. So eventually, the next year, my colleague Tim Coleman made these changes. And I must point out here that on the long run, this was actually the ideal solution for us EventStore, because we could just tell our customers to upgrade EventStoreDB and they would stop running into the issue. On the other hand, upgrading the file system would be much more risky for customers, and we definitely would not want to mess up someone's file system. And attempting to fix the bug in ZFS would also likely be hard. And furthermore, we would need to wait for a new package to be out, which can take a lot of time. So even up to now, actually, a package containing the fix is still not out. And another option could have been to build and roll out our own custom ZFS package, but maintaining it would consume resources. And so at that time, to immediately address the issue, the best bet was to find a workaround in ZFS that we could readily apply to our cloud servers if needed in an emergency, but it required a deeper understanding of the problem. So my hypothesis at that point was that there was something else happening in ZFS during the time that the msync was waiting in this wait and page write back function that we saw earlier. So over the course of the next month, I collected multiple tracers with the hope of finding some clues. And the problem with it is that the tracers are extremely large if you don't apply a filter. So multiple gigabytes per minute. And I remember having to analyze trace files that were around 400 gigabytes large. It was extremely time consuming to process them. And the tracers eventually made me realize that my hypothesis was wrong. No heavy operation was actually being done during the time that the msync or the wait and page write back function was waiting. So it was something else, not a heavy operation. And in parallel, I attempted to find a minimal reproduction of the problem in C. And the advantage is that if we were able to find one, first of all, it would easily allow us to replicate the problem whenever we wanted, and to also, secondly, to better understand it. And thirdly, we could also easily verify if the problem was fixed later once we had a patch. So I tried the above code, which simply simulates an msync of a small file similar to what a checkpoint does in an infinite loop, and ran the code over the course of several days. But surprisingly, the issue was not happening, and something was probably missing from the equation, and we'll see in a moment what it was. So I'll just walk you through the example quickly. So first, we open a file called repro_file. We memory map it, and then within an infinite loop, we increment a number at the memory location where the file has been mapped into the address space. And then we call msync to flush the value to the file. So it would just continuously write a number to the file, update it, basically update the file and flush it continuously. So it was almost identical to what the checkpoints were doing, but the problem was not happening in these cases. It was always doing it quickly. So after almost 1 month of trial and error and nearly losing hope, I stumbled across some settings in the kernel that are related to page writebacks. So I get back to what this is in a moment. So I had seen these settings earlier, but did not investigate too much. And I gave them a second chance and reduced some of these settings to the smallest possible values to make these kernel page writebacks happen more often. And then I launched my minimal C reproduction. And to my surprise, it worked. So I was extremely relieved at this point, knowing that this was the root cause. This was very likely the root cause, and the most difficult part was done. So basically, the Linux kernel periodically writes dirty pages, that is, pages that have been modified, but not yet written back to disk. So the kernel would periodically write these pages based on some thresholds back to the disk. But these dirty page writebacks happen very rarely in practice. So, which explains why we were seeing the issue so rarely. And then by adjusting the above thresholds, it was possible to actually make the issue happen much, much more frequently. So now that we can consistently reproduce the issue, we can dig further to see how exactly this affects ZFS. And so I posted a comment detailing the reproduction of the issue. And I don't remember getting, I think some people might have given some feedback back then, but we still continue the investigation. And at this point, we also had a workaround. After some experimentation, I found out that if you actually change this timeout, ZFS TXG timeout, to 1 second instead of the default 5 seconds, it was making the problem happen. It was still happening, but the delay was up to 1 second instead of higher as we were seeing before. So this workaround was not ideal because it would cause much more I/O to happen. Basically, it meant that data would be flushed to the disk every 1 second. And thus, I decided to investigate a bit further to understand the issue more deeply. So now in the next 2 slides, we'll explain what exactly is happening in the ZFS subsystem. So there are 2 types of writes in ZFS, sync writes and async writes. And so sync writes are critical writes that immediately need to go to the disk. They are important stuff. And async writes are those that are not critical and don't immediately need to go to the disk. So by default, async writes are flushed to the disk after 5 seconds in ZFS. And in event store DB, we use synchronous writes because we need to make sure that the data is on the disk when we acknowledge receipt of an event to avoid any data loss. And the way we do that is exactly with the msync function for memory mapped files, or the fsync function with the fsync system call with normal files. So essentially what was happening is that somehow the dirty page writebacks triggered by the kernel were causing flushing of the writer checkpoint file to be treated as async writes instead of sync writes. And thus they were being flushed to the disk after up to 5 seconds, causing the delay. So in this diagram, I tried to explain it in a bit more detail. So on the left, as you can see memory pages on the whole system, not just those belonging to event store DB. And the green rectangles are clean pages, and those in red are the dirty pages. That is, they have been modified in memory, but not yet written to disk. So in the middle is a transaction group where multiple async writes will be aggregated before being written after 5 seconds to the disk on the right. And so the scenario is as follows. when one of the thresholds in the kernel is reached, the dirty page write back thresholds, so a background page write back is triggered, which writes all the dirty pages on the system asynchronously to the disk. So it's important to note here that the kernel the kernel page writebacks are done asynchronously. So it happens at that point that the memory map writer checkpoint page was also dirty at that time, because say we had just updated the checkpoint but had not yet flushed it to disk. So all of these writes, including the writer checkpoint, go through the ZFS async code path into a transaction group, which will be returned to disk after 5 seconds, because the kernel thinks that these are not critical writes, so it's done asynchronously. So pages have several flags, and one of them is PG underscore writeback, which indicates that a page is currently being written back to disk. So the PG writeback bit, marked in yellow, is set on these dirty pages, but the flag will be cleared only after 5 seconds, after the data has been returned to disk. And now in parallel, event store DB does not know about all of this, and it's just trying to do an msync of the writer checkpoint file as usual. But the way the ZFS code was previously designed, now msync needed to wait for that flag, the PG writeback flag, to be unset before it could complete. So basically, it's waiting for the async write that was initiated by the kernel to complete. And after up to 5 seconds, the write completes, since the transaction group is written to the disk. And this unsets the PG writeback flag, which allows the msync call to complete. So to summarize, what's happening is that the kernel triggered an async page writeback of the writer checkpoint file. And now when event store DB calls msync to flush the writer checkpoint file, due to the way the previous code was designed, we needed to wait for this async write to complete, which could take up to 5 seconds. And so now that we understand the problem a bit more, this is the initial screenshot which showed the msync function trace. Now it will make a bit more sense. Basically, the wait and page bit function is waiting for the PG writeback bit to be unset during the msync call. So I'll just quickly walk you through the steps again, because I know it may be a bit confusing or difficult to grasp. So the scenario was that the kernel will first trigger a dirty page writeback, and so which will write all the dirty pages on the system asynchronously to the disk. And at that point, it happens that the memory map writer checkpoint page was also dirty, because we had updated the checkpoint but not yet flushed it. So all of these writes go through the ZFS async code path. And when the PG writeback flag is set on these pages, now event store DB does not know about all of this and tries to do an msync, but now it needs to wait for that flag to be unset. And it happens after 5 seconds when the transaction group is returned to the disk. And now the msync function can complete instead of blocking on the wait and page bit function. So wait and page bit here is the function that the msync was blocking on to just to wait for the flag to be unset, the PG writeback flag. So now some of the challenges that I had to work on a patch were, it was the first time that I was reading kernel and ZFS code, and it's really, really complex. And secondly, finding an elegant solution to the problem was not easy. I was at first considering using an unused flag on the pages, but it did not work out too nicely. So after some trial and error, I finally settled on using 2 counters to keep track of sync writes and async writes on each file. So here's a small part of the patch which explains the basic idea behind the solution. So each time an async write occurs to the file, we increment a counter and call Z async writes count. And when this async write completes, then we decrement it. And similarly, when a synchronous write occurs to a file, the synchronous counter Z underscore sync writes count is incremented, and it's decremented when the synchronous write completes. So keeping track of these counts allows us to determine if there are any overlapping synchronous and asynchronous writes just by checking if the other value is greater than 0. So if there's an overlapping asynchronous write, we immediately commit the write instead of waiting for the transaction group to close, which can take up to 5 seconds, as we said earlier. And so we basically prioritize synchronous writes over asynchronous writes when both of them are happening simultaneously. So that was the basic idea behind the patch. And roughly 1 week later, I opened a pull request on the OpenZFS repository. And after a lot of iterations and 1 more week, it was ready for review. And after a few months, the pull request was reviewed by Brian Behlendorf, the maintainer of OpenZFS. And I thank him for having taken the patience to review the PR. The review was very rigorous. He made at least 4 passes on the code before approving it. And roughly 1 week later, the PR was finally approved and merged. So here are some lessons that I've learned from this adventure. First, don't be afraid of things that seem to be hard. Things are difficult only the first time that you do it, then it becomes easier with time. Secondly, don't give up, particularly if the stakes are high. In this case, hopefully the bug will not only help us, but potentially other projects that use memory map files on ZFS. And third, learn things deeply, not only at the surface. And finally, the beauty of open source. It's really beautiful that anybody around the world can look at code that has been developed by some of the best programmers around the world, learn from it, and contribute to it. So that's it. I hope that you enjoyed the talk, and thanks very much for attending. So if you have any questions or if anything was not clear, feel free to ask. We have 10 to 15 minutes left.
Thank you so much, Shaan. That was super interesting. Thank you for sharing your adventure, and there was certainly some good lessons learned there. So thank you so much for sharing. We haven't got any questions currently. If anyone does have any questions after the webinar, please contact me and Shaan, and we will answer them for you. But we will send out this recording as well, most likely next week. So again, if you have any questions after you've watched it again, then please just let us know. But if not, I want to say thank you so much, Shaan. And yeah, hopefully see you all again soon.
Yeah, thanks. I would also just like to thank my friend Ludovic Avis, who helped me with the setup today. I'm really grateful to him for it. Yeah.
Thanks from me as
well. Thanks very much to you too, Natasha.
No worries. Thanks ever so much, Shaan. Thanks everyone for attending.
Thanks. Bye.
Bye.